Pluto is a remote and enigmatic dwarf planet that was once a part of our solar system's planetary group. However, recent surprising announcements by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight with a startling discovery. They suggested that the icy world is on a potential collision trajectory with Neptune. But how could this occur, and what would be the repercussions of such a colossal event? Are we witnessing a rare astronomical phenomenon, or is there something more to this looming cosmic clash? Join us as we examine the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, partly due to its unusual orbit, remains a subject of intrigue and research in the astronomical community. According to recent forecasts by leading scientists, Pluto's trajectory is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku raising the alarm about a possible perilous collision between these two planets that could present a significant threat to Earth. What makes such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one complete revolution. But the fascination doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating notably from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying our expectations based on their positions in the solar system. This leads to the natural inquiry as to why Pluto has not collided with Neptune. The solution lies in the effects of other planets' gravitational pull. Soon after research into Pluto's orbit began following its initial discovery, astronomers struggled to understand its unique trajectory. Unlike the other planets that have orbits relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened when it became clear that Pluto's orbit actually crosses over Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacy of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and impact one another with their gravity. It's like trying to predict, based on where they are now, where they will go, and how they work together. In Pluto's case, this problem shows how the paths of Neptune and the Sun's gravity all interact in a complex way. The terms, along with AU, vibration and latitude vibration with the VSSK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is AU vibration. In the context of Pluto and Neptune, this term means that whenever Pluto enters the orbit of Neptune, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from aligning. Latitude vibration, on the other hand, refers to the vertical movement of an object in space in its orbit. For Pluto, this means that when it comes closest to Neptune or any other huge planet, it is situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VSSK oscillation, named after three scientists, von Zippel, Chi, and LV, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. They move differently in this pulling. In Pluto's case, the VSSK oscillation helps us comprehend why its course around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly for a long time. The VSSK oscillation shows that even if things in space seem wild, some patterns and rules remain, keeping everything in its proper place. These components help keep Pluto's orbit stable, preventing it from colliding with Neptune or getting thrown off course. This three-body problem helps in understanding how these parts change because of how these objects in space pull on each other. Other benefits from studying this. Pluto's distant worlds are in our solar system and they're stars. Numerical simulations in the late 1980s revealed that, despite Pluto's orbit being technically chaotic with minor deviations in initial conditions leading to significant differences over millions of years, these distinctive properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the large planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection aids in maintaining Pluto's path steady. But Neptune isn't the only one assisting. Jupiter's gravity also contributes a significant role in keeping Pluto's orbit safe and stable, and Saturn assists a little bit more. These tests demonstrate Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a very long time, including billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to ensure Pluto keeps moving safely in space without running into any problems. These phenomena play a crucial role in the context of the universe for maintaining the order and predictability of space bodies' actions. In the absence of these mechanisms, the solar system as we know it would be a much more disorderly and unpredictable place. Pluto-like bodies could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. Particularly with regard to Pluto, discussions about it possibly crashing into Neptune in the future make understanding its orbit really important. This reveals the solar system's dynamic nature more clearly. The case of Pluto illustrates how even the most implausible unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the cosmos. Investigating the depths of space often leads us to deal with the unpredictability of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to a celestial body's delicate dependence on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's velocity or position can significantly alter its long-term orbit. Utilizing computer simulations has been extremely useful for researchers to determine how Pluto moves in space. These simulations use complex math to replicate how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even minor adjustments can make a big difference in where Pluto goes. These simulations began in the late 1980s and revealed an extremely intriguing fact about Pluto's path. Even though it has factors like AU vibration and latitude vibration to keep it steady, its orbit can still be quite wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how quickly it has moved, over many years its path can end up looking really different. However, despite all of this chaos, Pluto's orbit remains stable for a very long time, like billions of years. This means Pluto's orbit around the Sun involves a kind of order to it, even though it seems initially all over the place. Predicting cosmic events, especially when they involve erratic orbits like those of Pluto, presents significant obstacles. The inherent unpredictability of these systems indicates that forecasts for the long term are frequently rife with uncertainties, whereas numerical simulations offer a powerful means to understand and anticipate the upcoming paths taken by celestial bodies. They also draw attention to the limitations in our predictive capabilities. These models rely heavily on the accuracy of initial conditions. The intricate nature of the interactions they imitate means that any insignificant error or oversimplification can result in significantly diverse outcomes, making precise predictions a difficult task. In addition, the nature of celestial orbital chaos, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have advanced significantly in understanding space, the case of Pluto reminds us how our understanding of the universe still remains limited. Understanding the effects of the gravity of the giant planets on Pluto's orbit provides useful information about the broader aspects of the solar system's dynamics. It demonstrates how the position and presence of each planet has the potential to have effects that impact the stability and the paths taken by other bodies within the system. Therefore, why are prominent astrophysicists just recently raising concerns regarding a possible collision between Pluto and Neptune? Despite all of these complicated forces, Neptune endeavors to prevent such an event. Neil deGrasse Tyson, an important and well-known astrophysicist, contributes to the spread of astronomy and gives a different perspective on the mysteries surrounding the solar system, particularly the intriguing case of Pluto. Tyson, best known for his part in Pluto's reclassification from a planet to a dwarf planet, provides valuable commentary on the evolving nature of the public's fascination with the unknown realms of space and the mechanics of the heavens. Tyson's position regarding Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a punishment, but as a necessary adaptation to our expanding knowledge of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of ongoing education and adaptation. He recognizes that the difficulties of orbits like Pluto's serve as a reminder of how much there is still to discover in space. The enchantment of these unknowns, especially the potential interactions that occur between Neptune and Pluto, highlights the unpredictable and dynamic nature of our solar system. His work emphasizes the fact that the more we learn, the more questions arise regarding space, encouraging us to investigate and refine our understanding of the cosmos. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, concentrating on the unpredictable forces that make the universe what it is. Kaku is known for his ability to bridge complex scientific concepts and futuristic visions, making him a significant voice in discussions about the mechanics of the universe and the broader implications for humanity. Kaku's views on Pluto and its orbit emphasize the necessity of ongoing observation and sophisticated modeling to anticipate and understand potential cosmic events. He sees the interactions between planets and stars as a crucial area of study, not just for academic purposes, but for the practical implications. Pluto's potential collision with Neptune, for instance, is not just a theoretical scenario, but a reminder of the fluid and frequently chaotic nature of space. Kaku's futurist outlook pushes us to consider the broader repercussions of such events, from the impact on our understanding of the solar system to the potential need for future space interventions. His perspective emphasizes the significance of being prepared for the unexpected in space. According to his work, the better we understand the forces at play, the better equipped we will be to navigate and possibly lessen the negative effects of cosmic happenings. Tyson and Kaku's points of view agree that space is a realm of endless discovery and that our current understanding, while vast, is still limited. Their focus on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only comprehending the current state of the universe's mechanics, but also anticipating potential shifts in the future. The possibility of a collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the necessity for robust scientific inquiry, advanced technology, and the ability to adapt our comprehension as brand new information emerges. For Tyson and Kaku, the mysteries of space, as shown by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is general agreement among scientists that, in the not-too-distant future, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance, as well as a variety of gravitational influences acting on them. Therefore, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and possible disturbances in orbital dynamics mean that astronomers must keep an eye on and learn more about these celestial bodies to understand their long-term behavior and any potential risks they might pose. In contrast, the scenario of a Pluto and Neptune collision is speculative and considered improbable with current understanding. It underscores the importance of continuous research and advances in observational astronomy technology, including improved telescopes. Likewise, computer simulations will assist astronomers as models are improved and predictions for our continued existence will remain informed about the environment and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential collision scenario, while bringing attention to the complex and dynamic interactions within our solar system, ultimately brings to mind the vast, still new horizons for us in our understanding of space. Through ongoing research and observation, we endeavor to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving cosmos. The study of Pluto's orbit also opens up broader discussions about the solar system's stability. The relationship between Neptune and Pluto is fascinating because it is governed by gravitational interactions among each and every celestial body in our cosmic neighborhood. Each moon, dwarf planet, and planet is in a delicate balance, where their movements and positions interact in ways that occasionally appear counterintuitive. This complexity challenges our understanding of what is stable and what is not in space. Astronomers constantly face the difficulty of making long-term predictions about orbital behavior because even minute changes can reverberate throughout space for billions of years. Despite Pluto's apparently unpredictable path at first glance, the cosmic forces at play ensure that these bodies remain in a state of harmony for extremely long periods. However, even a small change in the orbit of a planet, or an unexpected gravitational force from another celestial body, could perturb this equilibrium. Such a situation could alter the course of planets, moons, and even the creation of tiny planets like Pluto, causing ripple effects throughout the solar system. Because of this, it continues to be crucial for scientists to keep refining their models and studying the movements of these distant worlds, ensuring that they are prepared for any unforeseen cosmic shifts that could happen, no matter how unlikely. Through this continuous observation, we come closer to a more in-depth understanding of the universe.